Hi, I'm Paul from Test Data Services, and this video follows on from the previous one where we ran a load test that pushed the system right to the edge of a performance disaster, but we held it there for about 2 or 3 minutes, and when we did that we were able to just see it teetering on the edge of really degrading badly, with keeping the response times to under a half a second instead of seeing them blow out to multi-second. The advantage of doing this was that we were able to keep the workload on the system. When we run a system too hard and we cause it to slow down too much, then all of the virtual users spend their time waiting and the actual workload drops off. I had enough iteration pacing in there to be able to support a substantial increase in response times while still maintaining the number of transactions per second. So transactions per second here is in green from that previous test run, and we saw that we stayed between 3,400 and 4,000 per second even when our response times degraded. And part of that was because we dropped some of our users as well, just to stop it from degrading too severely. So that's what happened. And when we did that test, we found that the performance of DynamoDB gets and puts was pretty well flatline, but our Lambda concurrency did go up, and our Lambda latency, the actual response times, went up. Now, the other thing to note is that the way that we collect the data direct from AWS CloudWatch is we're doing a statistics call as per one of the previous videos that you can go through, and it fetches the data every minute effectively, because that's the granularity of AWS CloudWatch for all of these type of metrics. The problem then is that if we fetch it every minute, then that means this data is really a minute old by the time we're representing it. So that's important we have to consider that we need to really shift this back left. It's a different shift left. So we actually start this, we would see this when it say went to 300 milliseconds of latency at 1431. It was really doing that at 1430 and 30 seconds. Sorry, 1451, 1450 and 30 seconds. So here. So this line really should be shifted by about a minute this way. When we look at that, that's another reason why I wanted to keep this running at that level of load for several minutes so that we had a chance to capture that. So that's those quick things I wanted to mention from before. Now, there were two issues, as it turns out, in the test. One was that in the script, which I reviewed, and if you go back and look at the artifact review video, I think it's video 3, you'll be able to see that when I reviewed it, this was the code for doing an authorize. Now, what's the difference between this and this? I forgot to put HTTPS. When I forget to put HTTPS in here, this script, dev-web script, will very nicely issue an HTTP request, and it will redirect to HTTPS, and then we'll have our HTTP request, which does its thing, and this is an authorized code flow step which actually fires off a redirect. So I was expecting a number of redirects anyway. Having a lot of redirects was not something that was out of the ordinary at all. So we had 2 redirects in this case. Now, the load generators that I had set up were set up and sized for a certain amount of capacity. So when I was doing more redirects than I was supposed to, and the requests per second were higher than they were intended to be, I think at that high level of load, I was causing an extra testing artifact that shouldn't have been there. And I'm not 100% convinced that even the AWS endpoint was actually handling all of those extra requests particularly well. So that was part of the reason we had a slowdown in response time that was not accounted for in the Lambda time. But the other problem, so to fix this, all I had to do was type in HTTPS, and it was in 2 places. Doing that, and now we get rid of that extra redirect. So I fixed that up for the test you're about to see. But the other thing I did was in relation to hot segments. So I'll show you this from the AWS website. So when DynamoDB needs to do updates and reads at very high rates. The way it achieves that is by having spreading the work across a number of partitions. And the partitions are keyed based on the actual primary key that you use. So I've done my design of all of the OpenID Connect stuff very nicely with random values, so they'll distribute very evenly. But that first test, the 6200 one we just saw, was using a single OpenID Connect client ID. So whenever we interact with that, the design is to do an update on a primary record for that client ID. You can do lots of reads, but when you're doing an update, even if you've provisioned 20,000 or 50,000 or 100,000 writes per second, it only lets you do 1,000 writes per second on a single partition. So if you do more than that, you'll start to get throttling occurring. And throttling is a bit nasty. If you do 1,001 attempts in 1 second, on that 1,001th, you'll get an error back. And that started to mess things up as well. So we didn't actually see a slowdown in performance, but we started to see other behavior. Now, there might be some sort of retry or something going on, I'm not quite sure. But to isolate that out from this next test, I updated the script to use 10 different client IDs. So this was the original code here. I changed that to use parameters. So in a dev web script, we can set up parameters. And in this case, I've got a subscription, client ID, and base 64 auth. And the client ID, when I use that, will base its value on the subscription, whatever was the subscription one, and the subscription value is set to be random. So what this means is it will randomly choose any of these client IDs. So when we are hitting DynamoDB to do updates in the database, we're effectively spreading those updates over 10 different partitions. So this test you're about to see is with 10 different client IDs, and it runs through to the full workload of over 1,000 virtual users without that extra redirect issue, and without any hot segments. What we'll then do after that is another run, and I will skew this so that I'll make it so that I have this top one, for example, represented in this parameter file many more times, like maybe an extra 10 times. If it was an extra 10 times, that means I've got basically a 50% chance of getting this one client ID compared with the others. So I'll be skewing them, and I might tune that, do a few shakeout tests, and then do another video with a test that actually shows one of these hot partitions, and then what we can do about that hot partition. So now we'll go forward to the video, which I've recorded for the actual rerun of this test. I'm going to just start this off first, then I'll talk about it. I'm going to launch 52 load generators here. And as they launch, I'll show you in this console view them popping up. So you can see that they're launching, and I'm running this for real right now in front of you. So we can see these running, and like the previous video, this time I know how to quickly show you what the status is of an instance when it's coming up. Just go to status instance screenshot, and when we see this, we know that we're not ready to log in, and therefore all of the apps on the actual instance aren't ready to accept load. So the load generator agent won't be able to run. And we're now approaching 5,000 users, so we're at 4,860. We can see that our concurrent lambdas is now heading up close to 200. We're at 190. Response times are all pretty well flat, as we would expect. Total transactions per passed per second are at 3,000. We're doing about 3,500 requests per second, which each of those are an endpoint call. Like I said yesterday, you might remember that I'm collecting these stats 3 times a minute, every 20 seconds, and we can see here slight changes, and that's because the stats seem to take a little while to come in. I was looking at them just before starting the video, and we can get like 50,000-60,000 data points in a 1 minute period, but some of those trickle through in the following minute. So that's why it's good if you do this approach to get the stats multiple times in a minute. It also explains why that there are issues trying to get granularity of better than a minute. Now we've passed the point we got to yesterday. A little glitch there, just to remind us of yesterday, maybe. But so far so good. We're at 6,500 users now, doing 4,500 hits per second. Starting to have a bit of a slowdown here. Look, I might pause it. We'll just let it settle for a little bit. Have got a few errors here. Let's have a look at the transactions per second coming through. It's a nice little thing here. So we're doing 2,170 token refreshes per second. We're getting 90 new unique random identities per second. We're doing for users that are repeat visiting about 450 authorizers per second, and then about 5 times that number of subsequent refreshes. We're now at 380 concurrent lambdas. Response time is still pretty good. We're at nearly 8,000 users, which is great. We're doing about 5,600 hits per second, which is nice. Bandwidth is pretty low. We're supposed to talk to AWS if we do a very high bandwidth test, but I'm pretty sure bandwidth is very low. Let's just drag this down here and have a look. Yep, so we're only doing 8 megabytes a second, so nothing. Which is good. Starting to just have a slight slowdown in response times here. We're at 8,600 users. We're now doing over 400 concurrent lambdas. So we've got 400 transactions across all of the different calls in flight at the same time in Lambda. And in the previous video, I mentioned 1,000 limit. That's a default starting limit of 1,000. If you've got a proper account that's processing production workload, you can ask for that to be increased to 2, 3, or even 4,000. And I think quite a lot of organizations actually do that instead of tuning. And as you saw yesterday, the moment you have something start to go wrong and your response time blows out on one of those lambdas, then your concurrency goes through the roof. You don't fix that by just increasing the number of lambdas you're allowed to have running concurrently. What you need to do is address why they're slowing down. All right, 9,800. I think we're going to make it to, we're starting to slow down here, but let's see how close we get. We're at 460 concurrent lambdas. We're now over 10,000 users. It's sort of nice to hit that 10,000 point. Now we're at a nice symmetrical number, 10201, which I thought was a sort of a cute thing to do. We'll let this sit here for a little while, burning through transactions. We've done 1.8 million. And 1.9 million. Response times are still averaging under 0.3 seconds, which is great. So what I might show you while we're sitting here waiting is, if we look at some of the maximums, let's look at update, because we didn't do that yesterday. So I've just got to focus down here. DynamoDB and get latency. I want the user one, users get put update. Okay, so this is the update latency average right down the bottom here at 4 milliseconds. But if we have a look at maximum, so each minute, look at that. So the time it took to write updates peaked at 690 milliseconds during that minute. And you can see it's gradually sort of been edging up over the course of this test run. So the good thing is, I have been able to effectively shake out the issues from the previous test in this one. Pretty confident that I've got a good solid test. I actually need to consider pushing it harder to see how hard we can go. And to do that, I'll actually need to use slightly bigger load generators or more load generators. Maybe I'll just go for more. It's pretty easy to do that. Actually, I'll just stop the test now, do some analysis, and if I need to, I'll just add to the video with a bit more analysis afterwards. So the test's finished. I've started up analysis. I've had a quick look through it, and now I'll walk you through. As we can see, we got to 10201 users, so just over 10,200 users. We did 5 gig of data, not very much really. We did this. These are the different transaction names. I didn't put an SLA in. 90th percentile was all pretty good. We had a few errors. I'll go through them later. We had a total of 10 HTTP 500 errors. And I'll just step you through each of the graphs in the analysis. Let's just change the granularity of this one because we can make it a bit nicer. That was a little pause in ramp up there. So we can see we did pretty well, a full ramp up, stopping the test at 1346. Hits per second followed that same track up to about 7,300 per second. Throughput, we went up to about 10 megabytes a second, 80 megabits-ish per second, which is fine. Average response times, nice and flat with an ever so slight degradation. This is a 2-second scale. We had a few little spikes here. Not sure what's going on with them, but they were at pretty high load. Total transactions per second heading towards 6,500. OpenID Connect transactions per second close to 5,000, so that's quite a bit. Lambda concurrency, so this is from the monitoring direct out of AWS's CloudWatch. This top line is the total concurrency across all of the lambdas that I was monitoring. So we got up to about close to 600, very close to 600. This one here is all of the OpenID Connect calls. This one is the most dominant call, so doing token exchanges. So in OpenID Connect, we do token exchanges as part of a code authorization flow login, and also when we do a refresh token. So that's the bulk of transactions was supported by this Lambda, and that's why we were running at over 330 or so per second, like constant concurrency. All the others here add up together, account for the difference between this one and this one. So that's Lambda concurrency. DynamoDB gets, we can see early on 4 or 5 milliseconds, but as we ramp up load, like normal, AWS, the platform itself, really speeds up, and we're down to 2 milliseconds for most of our test. The time taken to do updates was generally very fast, with averages of around 3 milliseconds. But one thing you don't get after the event easily, I'm not even sure you can get it for all the metrics, is this maximum figure. So you can get it at the time, but I can't see in CloudWatch how to actually fetch these maximums. So it's sort of quite nice when we see, in this case, 0.7 of a second latency on the maximum. In that minute, we might have had 1 or we might have had 10 out of thousands, but it's still nice to see that. Put latency, super good the whole way through. Lambda latency was between 40 and 140 milliseconds across all of them the whole way through. They didn't slow down at all. API gateway integration latency was solid the whole way through as well. So this graph here shows total transactions per second ramping up till we held off about here, and we can see at the same time on this graph the response time. So when we got close to 10,000 users, or near 7,000 transactions per second, we did start to slow down. But note here we've got a few spikes. I don't really like spikes. They're not big. And when we have these spikes like this, sometimes it's a bit hard to see what's really going on. And that's because we've got so many transactions per second, like many hundreds of transactions per second for each of these transactions. It means we get an average. Now we've got 50 load generators, or 52 load generators. What we can do to give us much better insight, this is really amazing, watch this. We can filter these results by host. So when I do this, see how much more information we get when this screen refreshes. Wow, look at that. So what we've now got is all of these transactions per second showing up. So I might actually flip away from that screen because it's not really giving me what I was hoping to see. This is without the transactions per second. Let's flip this one across to hosts as well. So we're going to get the response time for each of the transactions for each of the load generators, or hosts they're called. Watch the scale here. So now we can see that across the test, we had occasions where the odd response was much higher than average, but it didn't really reflect as one of those spikes. But we can see little areas like here and here where we actually had multiple all at the same time. And over here, we've got this big mess because what's probably happened is a small percentage of transactions will have been very slow and a number will be very fast. Which takes us to the next point. For the next test, like I said in the introduction, I plan to run a test with a skewed number of OpenID Connect client IDs so that I can get a hot segment in DynamoDB. Now, the point of doing that is so that we can actually see it and troubleshoot it and diagnose it and then maybe rectify it. So what I'll probably do is I'll probably add in some extra instrumentation. I might use Amazon's X-Ray product, and I'll put some special start and end markers. But with X-Ray, you can nominate the percentage of transactions that you want to catch. Now that we've seen this over here, I think I'll set at least 10%. The temptation is when we're doing millions of transactions in a short time to maybe just do 1%. But if I only do 1% of X-Ray, I may not see this. In this case, I'm showing every transaction and I'm seeing all of these slow ones. But if I just averaged out, by removing that filter group, if I just average this back to all of the load generators, we get that. Now, that's a different picture, right? So the sample rate for X-ray is very important, as is the way that we present things in these graphs, even in Load Runner. So there's a lot to be said for being able to separate out with granularity your results. So we can go by second. Some people I've seen with their tests won't use 1 second granularity. They might use, let's say 10 seconds granularity. Now with 10 second granularity, gee, you don't see any spikes at all, and you just see this little thing over here. If we now added in all of those load generators again, so host, then we'll hardly see anything. No, you don't see much at all. But the moment you change the granularity down to 1 and you have all of the load generators, you see all the noise, which from an analysis point of view is a bit too much to deal with. But from an awareness point of view, is very important, especially when we start to move into some detailed instrumentation that involves sampling. So I'm looking forward to doing the next video where we'll do some sampling, hopefully, and some X-ray, and we'll do some heavy-duty, hardcore performance engineering. Looking forward to it. See you then.